What causes fouling in mechanical cooling systems? Have you ever wondered why some cooling systems seem to struggle with efficiency over time? One of the main culprits is fouling, which can significantly impact performance. Let's break down what causes this issue in mechanical cooling systems. Fouling happens when unwanted materials build up on heat transfer surfaces. This buildup can block the flow of heat, making the system work harder and less efficiently. The accumulation occurs when the rate at which particles or substances settle on surfaces is higher than the rate at which they are removed. One common type of fouling is particulate fouling. This occurs when suspended solids, like dirt or rust particles, enter the cooling water and settle on heat exchanger surfaces. These particles can come from external sources, such as rivers or seawater, or from corrosion within the system itself. Another significant cause is biological fouling. Microorganisms, including algae and bacteria, can thrive on wet surfaces inside cooling systems. This growth forms a biofilm that not only blocks heat transfer but can also lead to corrosion and other operational challenges. Chemical scaling is another issue to consider. Dissolved minerals in water, such as calcium carbonate, can precipitate when temperature or pH levels change, leading to hard-scale deposits. This is especially common when water temperatures rise, promoting the deposition of salts. Organic fouling is also a concern, particularly in systems that handle organic fluids or food products. Substances like fats and sugars can stick to surfaces, creating deposits that hinder heat transfer. In colder environments, freezing or frosting can occur in air-cooled exchangers. Frost acts as an insulating layer, further reducing heat transfer efficiency. Larger debris, known as macro fouling, can also create problems. Items like leaves or algae mats can enter open cooling water circuits, causing blockages and uneven flow distribution. The condition of materials and surfaces plays a role too. Rough or corroded surfaces provide more area for deposits to stick, while the choice of materials can influence fouling tendencies. Operating conditions matter as well. Low fluid velocity can reduce the shear forces that help remove deposits. When fluids move slowly, the risk of fouling increases. High temperatures can accelerate both chemical reactions and biological growth, compounding the issue. From a design perspective, understanding these causes is essential. Mechanical engineers can select appropriate materials and design flow rates to minimize fouling. For instance, maintaining higher fluid velocities can help reduce particulate and biological fouling by increasing shear stress that removes deposits. Controlling water chemistry, such as pH and hardness, is also important to prevent scaling. Regular maintenance and filtration can help manage particulate and macro fouling effectively. In practical cooling system design, engineers often include a fouling factor in heat exchanger calculations. This factor accounts for the additional thermal resistance caused by deposits, ensuring the system maintains performance over time. In summary, fouling in mechanical cooling systems arises from a mix of particulate matter, biological growth, chemical scaling, organic deposits, and environmental factors. Effective design and operation focus on controlling these elements to sustain efficient heat transfer.